Welcome back. We are in week 11 of inverse methods in heat transfer. In this video, I would like to give you a simple introduction to this week and also talk specifically about artificial neural networks as surrogate models. For the last several weeks, from week 8 to week 10, we have been looking at neural networks, and we have looked at, especially in the last week in detail, how the forward pass and the backward pass or the backpropagation algorithm works in neural networks. Now, specifically, a thing that I would like you to remember as we go through this week is remember that neural networks or artificial neural networks are functions. Okay, I emphasize this quite a lot over the last 2-3 weeks, but please do remember this, especially as we come to this portion, the physics-informed neural networks portion. Okay. This week, what we'll be looking at is how to use ANNs for inverse problems, and it is this property that helps us do this. This plus the fact that ANNs are universal approximators. Okay. So what this means is you can write any function you want, or you can approximate any function you want as an ANN. And in order to find out the parameters of the ANN, as we saw in the last 3 weeks, we solve inverse problems. So there is a tie-up with inverse methods in another fashion also. Okay, so this week we are looking at these 3 things. How to use ANNs as surrogate models, which I will discuss in this video. Then we will look at physics-informed neural networks, which are a way of using ANNs both to solve forward problems as well as inverse problems. You will see that when we try to solve ANNs as surrogate models, it requires a lot of conventional simulation, whereas when you use physics-informed neural networks, also now known as PINs, P-I-N-Ns, physics-informed neural networks, when we use these, you don't need any additional simulation in order to support your inverse problem solution. Now, we will be surveying primarily this week some research papers. I have written those papers down here, and I'll be showing you some of these papers even in this video. The purpose of these papers is to serve as an introduction to this field. Okay, I would encourage you to go online, see if you can download these papers. Unfortunately, I can't share these papers directly due to copyright violations. I will be showing, because that's apparently it's not a copyright violation to show. And you might have seen online, several people are do share papers. In fact, almost all of these papers, except for the first one, are available freely online on arXiv. The first paper here corresponds to using ANNs as surrogate models, which we look at within this video. And these 3 or 4 papers are related to using ANNs in order to define physics-informed neural networks. Okay. One last thing before we step into the problems, step into surrogate models this week. I will not be showing you codes. I had promised you in the last week that I would show you some of this programs even for last week as well as this week. This we'll be doing in the next week. This week, we will concentrate primarily on theory. There were some technical problems because of which I was not able to demonstrate the codes this week. We will stick with theory this week, and I will show you some demos, and primarily next week's videos will be geared towards showing you demos. So let's now step into the very first problem, which is how to use how to use ANNs as surrogate models. So let's look at that now. So ANNs as surrogate models. What does this mean? I'll show you by means of an example by reference to the Chanda et al. Paper. But let's first talk about the general problem and then come back to the specifics. So let's say you have a complicated domain. Okay. Complicated, let's even say a 3-dimensional domain. By a domain, I mean you have a 3-dimensional body. Okay, so there's a 3D body. And the inverse problem is as follows. Let's say you have, let me make this simple. Let's say we have a heat conduction problem. Okay, so this body, obviously, this is not the shape of any fin within a realistic domain. But let's say I'm just showing you a complex enough body so that it doesn't look like the solution is straightforward. So let's take a heat conduction problem. Let's say within a chip, you are trying to optimize thermal management of a chip and you want to optimize heat transfer from there. So unfortunately, you do not perfectly know the thermal conductivities of the material. Okay. So let's say that the material is what is known as anisotropic. Anisotropic means, and this is the paper that I'm going to show, X, Y, Z case behave differently. Okay, so this happens for composite materials. Some of you might be familiar with this from solid mechanics. But in general, assume that you have a material which does not behave in the same way in the 3 coordinate directions. That is, there are different material properties depending on which direction you are looking at as far as heat transfer is concerned. Just as an example, or just as clarification, for example, if it was isotropic, then K in each direction is the same. So we would say Kxx is the same as Kyy is the same as Kzz. And you would have something like del square T del X square plus del square T del Y square plus del square T del Z square equal to 0. Okay, so this is if it is isotropic. On the other hand, if it is anisotropic, then your property would look like, or your governing differential equation coming from energy would look like Kxx del square T del Y del X square plus Kyy del square T del Y square plus Kzz del square T del Z square equal to 0. So obviously, anisotropic goes to isotropic if Kxx equal to Kyy equal to Kzz. So in order to solve for temperature within this body here, you would have to solve this differential equation. So this differential equation is what will lead to the solution for temperatures here. Okay. Now, suppose I want to estimate our inverse problem. Our forward problem is, or let me write the forward problem first. So the forward problem would be given Kxx, Kyy, Kzz, find, let's say, heat transfer, or find the temperature distribution. Find temperature as a function of x, y, z. The inverse problem, I'll show you the mathematical formulation also a little bit later. The inverse problem is given T at some locations. Okay, so remember, we can only give this at a finite number of locations. For example, we could give locations such as this. Okay, so suppose I have 5 or 6 thermocouple sensors distributed across the body, even though it looks like it's within a plane. Remember, this is a 3D body. I could put my sensors anywhere. So given this at some xi or some I equal to 1, 2, 3, 4, how many ever sensors we have to estimate. We can't find, but we can estimate the property. Okay. Now, how would one go about this? So the normal procedure will require us to have a forward model. What is this forward model? Forward model solves the forward problem. That is, from Kxx, Kyy, Kzz, find T at xyz. Okay. Now, this is sort of a black box as we have been doing. So you have inputs Kxx, Kyy, Kzz, and these 3 go into the forward model. And what comes out is temperature at any XYZ that you wish to give. If you wish, we can add XI, YI, ZI here, and you get temperature at XI, YI, ZI. So the procedure is this: you need a forward model, then find KXX, KYY, KZZ that minimize. So let's call this T hat, that minimize our T hat minus T at these points square summed over all I. Okay, so you find the least square loss, you can divide by 2 and the number of points that we had, etc. Okay, so we want to find this out. And this is obviously an optimization problem. Now, if you remember all the hand-based calculations that we did, this is where they become important. Each forward calculation takes some effort. Of course, we took linear examples or a simple A times 1 minus e power minus bt or some such example. But the forward model for this 3D case is extremely complex. So unfortunately, the forward model is expensive. Why is it expensive? Because it requires a full CFD simulation. Now, since I have not talked about CFD within this course, I'll give you a small, very brief introduction to what CFD is. CFD, of course, stands for those of you who are familiar, computational fluid dynamics. Or, of course, you can have CHT, computational heat transfer, if you wish. But the standard name has always been computational fluid dynamics. Idea is simple. Idea is if you have an equation like KXX del square T del X square plus KYY del square T del Y square plus KZZ del square T del Z square, all these are replaced by discrete approximations. What's the example of a discrete approximation? So the idea is simple. If you have 2 points, let us say, and we are looking at a simple one-dimensional derivative dt dx, then since we have only information at finite number of points, let's say this is at xi, this is at xi plus some delta x, then you will say that dt dx is approximately t at xi plus delta x minus t at xi divided by delta x. Now, what this enables is that this whole equation, which is a complicated differential equation, now becomes a difference equation. For example, we can show, I am not showing this here, that d square t dx square. So this, of course, is just the slope. Similarly, d square t dx square can be approximated by t at xi plus delta x minus 2 times t at xi. You can basically take derivative of derivative and obtain this expression, xi minus delta x. So you need 3 points divided by delta x square. So this is, of course, approximate. Please remember this. This is not exact. Now, once you do this, this system basically becomes a system of linear equations. Why? Because all you will have is t at some point minus t at some other point plus t at some other point. It's just a combination of temperatures at a lot of places. Okay, so if you see here, typically what you would do is, let's say your domain looked something like this. You would put these grid points and you will start estimating temperatures here. But every temperature depends on every other temperature. Okay? Because the equations here, you will basically say that this is equal to 0. So you'll get a series of equations. I'm giving you just a brief idea here for intuition. Otherwise, please look up something called the finite difference method, which is the most intuitive method for computational fluid dynamics. You should be able to understand it in case this brief 2 to 3 minute introduction was not sufficient. So what you do is you create what is known as a mesh. Mesh consists of points where you wish to find out the temperature. And as you reduce delta X, your estimate T becomes more accurate. Okay, all this is to say that this forward model is expensive. Why is that? Because first, you will have to create a mesh. Next, you will have to solve for temperature at all points. Why? Because only when delta X becomes very small, your solution accuracy becomes very high. Once you do that, usually, sometimes you might have as many as million points. Even if you have 10 sensors here, in order to solve for the temperature there accurately from your forward model, you might require a million mesh points in order to obtain them. Okay, so let's say you have these sensors at all these points, you have ground truths T1, T2, T3, etc. You also want to make predictions from your computation T1 hat, T2 hat, etc. But in order to calculate T1 hat, T2 hat, you have to solve CFD for every iteration. If you are using an iterative method, and if it's a nonlinear problem as it was with Gauss-Newton, etc., you will have to solve for each iteration of Gauss-Newton, you will have to solve multiple, you need a CFD solution in order to get T hat. Since this is expensive, you cannot really use this in order to solve KXX, KYY, KZZ. Because you have multiple iterations, it takes a huge number of CFD simulations for a inverse problem. So huge CFD computation for inverse problems. If time permits, I'll show you an example of this in the next week. I'm not sure if there will be sufficient time for that. Okay. Now, here is where ANNs come to our rescue. Okay, so ANNs to the rescue. How so? So you use an approximate solution to the CFD computation. Okay. Now, how can we do this? The idea is like this. So this is what is known as a surrogate or a substitute model. A surrogate means a substitute. So the idea is this surrogate model should be cheaper than CFD. Okay. So how do we solve the inverse problem? Assume that we have some method of getting this. Okay. Assume we get some method of getting the surrogate model. Then what we do is we use the cheaper model here. You run a forward model, but you don't run CFD. You actually run the cheaper model and then iterate. Okay. So let me first show you how to get a surrogate. And this is where all that we did in the last few weeks comes to use. So how to get a surrogate using ANNs. So let us say we have used CFD solver, run multiple simulations. Okay, so we run multiple simulations with various KXX, KYY, and KZZ. So you put a whole bunch of KXX, KYY, KZZ, collect one second, collect T of some XY, Z at various points, and then use an ANN that takes KXX, KYY, KZZ, X, Y, Z as input and gives T of XYZ with KXX, KYY, KZZ as parameters. Okay. So in short, your network is going to look like this. It's going to look like KXX, KYY, KZZ, X, Y, Z. How many ever layers you want? It could be one layer, two layers, multiple layers, and it gives out one output, which is the temperature. So how do we train it? We do a simple standard supervised learning. The supervised learning is such that for a given KXX, KYY, KZZ and take multiple locations, you actually just need this, do a CFD simulation. From the CFD simulation, take ground truths from CFD. So you make a table, fix one KXX, KYY, KZZ, take multiple XYZs, measure temperatures there so that you get a huge data set of temperature versus KXX, KYY, KZZ, XYZ. Now train the model. The unknowns of the model are of course W's. Learn these. Now what happens is this process of collecting the data, all this process is of course expensive, but it is offline. Offline means we don't have to do it as we are collecting the experiments. You can do them just once. Once you do it, once you finish it, now what you will actually have is actual measurements. Okay, so now you do the experiment after having done the simulation. You build your model, you build your ANN model. Now you make some measurements. You make, let's say, 20 temperature measurements. You see those temperature measurements, 20 temperature measurements, and then solve an inverse problem. How do you solve the inverse problem? Guess for KXX, KYY, KZZ. Do a forward pass. The forward pass, however, should not be through CFD, but through the ANN, which is an approximation. It's a good enough approximation. So if you make a good approximate, it will do a forward pass through CFD, and I will demonstrate it to you next week for some of the simple problems that we have done earlier. So you do a forward pass through the CFD, and through that forward pass, you see, well, how much does T match T hat? T hat is, remember, through the ANN, through the surrogate model. T was through the experiment. You are making an experiment and trying to match this. Once you do that, you will see T hat doesn't match. Go back, correct KXX, KYY, KZ, and keep on doing. So note that there are two inverse problems being solved here. First inverse problem being solved is to approximate the CFD solutions and find W for the surrogate model. The second approximate. So this is, for example, this inverse problem is for the computation or for the forward model, and the next approximate is for the inverse model. Now, let me clarify this in case this is not clear. Let me clarify this by visiting the paper by Chanda et al. And hopefully this will become a little bit clearer. So here you can see this publication that I was referring to by Samarjit Chanda, Professor C. Balaji, Professor S.P. Venkatesan. And this work was done at IIT Madras a few years ago. Professor C. Balaji, of course, is a distinguished professor also at IIT Madras in the mechanical department. And Professor S.P. Venkatesan was also an ex-professor here. He's now retired. I think Samarjit Chanda, I'm not sure if he is a faculty member at IIT Palakkad, but he was at IIT Madras and a PhD student at the time that he wrote this paper. This is just a simple demonstration of how you can use ANNs very effectively in order to solve for inverse problems. The problem is somewhat similar to the one that I described. The geometry is a little bit simpler, but as you can see in the abstract here, this is basically the idea is to define or determine the thermal properties of a composite material. The typical composite material here would be, the assumption then is you are going to use it for aerospace or satellite applications, which is why a person from ISRO was also a joint author in this paper. So the idea was to determine both an experimental technique as well as an inverse estimation technique. I am not going to go over the experiment. You are welcome to look at the paper and search for this paper. The title is available right here for you. It was published in this reputed journal called IJTS, International Journal of Thermal Sciences. Professor C. Balaji is currently an editor, distinguished editor of this journal. Okay. So what was done was the property of a particular honeycomb composite being, for the purposes of this video, simply being something where you are going to have different anisotropic properties in each direction. Okay. In such a property, you basically want to determine the thermal conductivities. So they did a full-scale direct numerical simulation, which I didn't go over here, in order to understand the thermal transport process and determine its thermal conductivities. So this is a ground truth for thermal conductivities, but let's not look at that. For now, all they did was they developed an inverse methodology. I'll underline this. Okay. So the idea here was it required two different algorithms. One was an ANN and a genetic algorithm. This ANN is used, as I said just now, as a surrogate model. What is meant by a surrogate model? I just explained it. In case you want to run the forward pass really fast, you want to approximate the CFD results really fast in order to estimate the property. The genetic algorithm is what was used in order to estimate the optimization problem. The optimization problem or the inverse optimization problem. I'll come to this distinction later. I often find that the first time people look at it, they're a little bit confused, even though we have done exactly the same thing so far. So another way of looking at it is the ANN was used to serve the role of, remember, we had our expression like T hat equal to W0 plus W1X. Instead of that, we use an ANN because we actually don't know the analytical expression. We use an ANN there. So that was the role of the ANN. ANN was serving the role of the forward model. Now, when we do the correction, when we do the optimization, GA was used to use the same thing as what we used gradient descent for. Okay, gradient descent or Gauss-Newton. Instead of that, a different algorithm was used here, which is the genetic algorithm. So when you see genetic algorithm, just assume that we are doing something like Marquardt, Tikhonov regularization or Gauss-Newton. So those are the two relative roles of these two things. Okay, so I'll just come down here and show you where the forward problem is. So what we were looking at is design of an isotropic material of this sort and try to estimate the temperature distribution on the standard test sample. Okay, so the forward problem here is, remember, given kxx, kyy, kzz, find t. So that's what is written here. Remember, the inverse problem is given t, find kxx, kyy, kzz. So we are going the other way around in the forward problem. So as is written here, you want to estimate the temperature distribution given its thermal conductivities along the three principal directions. Okay, so the standard test sample is shown there. And of course, the equations are the same as what I showed earlier. Kxx del square t del x square plus kyy del square t del y square, etc., etc. And you are also given the boundary conditions, so which are of course essential in estimating the forward problem. Otherwise, you cannot really solve the forward problem. So you have insulation at a few ends. You have, and this place you have a free convective boundary, and here of course is insulation. And this is at the bottom side. You are providing some heat. Okay, so these details are unimportant as far as the course is concerned, but you can see the detail to which you need to give the model perfectly in order for you to solve it. Now, if I gave you this analytically, I gave you all these things A, B, C and asked you to solve analytically, you cannot solve it analytically because this is not something that you can easily solve. You will have to use some Fourier series, and even then, frankly, you will get only a few terms. So what we do is effectively what we are doing is approximating using ANNs. Now, there are two ways of approximating using ANNs. The first way to approximate using ANNs is solve the CFD solution. Okay, so that's what is done. You now discretize this. This is called turn it into discrete sets, which means you have this box. You put lots and lots of meshes. Okay, you put 3D meshes. And at all these points, you write a discrete version of the finite difference equation and you solve a linear system of equations. That is going to be a big linear system and it's going to be an expensive solution. Once you solve this, then you approximate it. So you make a table of various solutions. So basically what they did was for various values of kxx, kyy, and kzz, kxx, kyy, and kzz, they ran for various xyzs. Or they solved this problem and measured at various xyzs, made a giant data table. As far as I know, they ran 200 simulations. I will show you that later in the paper. They ran 200 simulations, collected all that data, and then approximated this data using ANNs. And we saw the process of approximation in great detail in the previous weeks. Okay, so once you approximate that, then you go ahead and solve the inverse problem. But first, let's see the forward problem and how we approximate it using ANNs. So this is what the setup looks like, the actual physical setup. Now I'll show you where they measured it also. This directly jumps into the inverse problem, but before I come there, you can see this. The finite difference of the forward problem is transformed into a feed forward backpropagation or artificial neural network. So this is where, so you can see that even this ANN can be used. We used gradient descent, but they used Liebenberg-Marquardt. So forget that. What this is doing is a simple thing. You are basically trying to find out the equivalent of t hat equal to W0 plus W1x. But the way you do that is take the finite difference solution, run many different solutions. How many? They took 200 data sets for various values of kxx, kyy, kzz, made a giant table. I'll show you some examples of some small tables in the next week, but they made a giant table, and all they did was they put a one hidden layer. Now they approximate the result of all this data collected using just 20 neurons. Turns out that is sufficient, which is remarkable actually. But for this range, it turns out it was just sufficient to run with this simple case. Okay, so once they did that, they now have a full ANN. Once you do that, you actually can now estimate the principal thermal conductivities of the test sample. Okay. Now, how do they do that? You see here, here's the setup. We actually now have a forward model. They did something slightly clever with the forward model compared to what I said, but let's forget that. They took a forward model, and the forward model is the ANN. Now, forget the ANN for now. Now, only assume that you have the forward model. How do we solve the inverse problem? We actually now have to measure temperatures. Just like in our slab problem, we were measuring 6 temperatures. Here, they measured, you can see, up to 32 temperatures. Okay. So let's say 32 temperatures or 19 temperatures or something around that. Okay. So they measure around 19 to 32 temperatures. I think I might be wrong, or it might be 19 temperatures or so. So they measured a certain number of temperatures. Now, all you need to do is to say that I want my model parameters. I want kxx, kyy, kzz such that t estimated is different from the ground truth. So T simulated basically is the ground truth, and T estimated is whatever we are predicting the temperature to be for this kxx, kyy, kzz. Okay. So the ground truth is the x. Oh, sorry, I think I used the notations wrong. TE in this paper, this is why it's important to know, is experimental, which is the ground truth. And here simulated is actually our estimate. or what we call T hat. So I'll just call it T hat here, just for your clarity. So you actually take the experimental temperature and then you take your model and ensure that the two of them are as close by as possible. Now, how do we do the model? We already know that for the model, if I give kxx, kyy, kzz, it can give me an estimate. Okay. So once you give an estimate, compare it with the actual experiment. If that doesn't work out, correct the model. Now, it is for this correction that they use genetic algorithms. Okay. So here is the whole flow chart. You start, you give some guess. This you will see is the standard inverse process. You have a trained artificial neural network. Once again, I'll emphasize this is simply a surrogate forward model. If you had huge computer power, you don't need an ANN. Okay. All you need to do is run the full CFD. Okay. If you don't want to run the CFD, you run an ANN. You run the ANN, this ANN gives you TS. You have experiments. Okay, you just conducted the experiment that gives you TE. Now, once this doesn't match, if it is not lesser than a specific error that we want, then you correct. So the Gauss genetic algorithm is for correction, basically for optimization. So forget all that because we did not do genetic algorithms here, but suffice it to say that genetic algorithms are basically just an optimization algorithm. Instead of Gauss-Newton or gradient descent, we use genetic. That generates the next guess, just like we had W equal to, or Kxx would be equal to Kxx minus alpha del J del Kxx. Instead of that, genetic algorithm has a different way of getting there. That next I'll guess goes to the ANN and it goes here and you keep on going in the cycle till you get some optimal Kxx, Kyy, Kzz. So in this video, we saw that a fairly practical problem, and this can be utilized in various practical problems. You can actually use ANNs as a substitute in order to, instead of simulations, in order to guess the forward model, you can use ANNs to guess the forward model. As I said, I'll show you a very simple example of this in the next week's simulation. But is this the best that we can do? It turns out you can do something even more clever, which is where we come to physics-informed neural networks. And I will demonstrate that, or I'll talk about that in the next week, next video. Thank you.